November 2020, and we are back with another SecTalks Sydney session. Welcome, everyone. This is our session number 43 in hex or 62 in decimal. We are back with two presentations tonight, one from the past CTF winner, and the other talk, our main presentation from Dr. Yuval, which I will be introducing both speakers a bit later. Now, like always, you can use the IRC channel, the SecTalks Sydney channel on the Slack, and the YouTube live chat to ask your questions. Both our speakers are happy to take your questions as they go through the presentation. And like previous years, we conclude SecTalks in every year on November, and we restart February the next year, similar to this year. So this will be our last session for 2020. Before we start the presentation, you most likely have seen the feedback form. This is our yearly feedback form that every year we ask you guys to let us know about your thoughts about how the SecTalks was in the past year and what you would like to see in the coming year in terms of the talks, people that we should invite to SecTalks to do the presentation, or if you like to help us running SecTalks, you can capture all this information in the feedback form that we have. You will see the link to the feedback form also during the session tonight. Otherwise, go to the meetup page and you can find the links there. Well, without further ado, I will now pass the presentation, the stage to Ben. He will be talking about his walkthrough of the past CTF and the solution that he came up with. Ben, the stage is yours.
Hey guys, welcome. Okay, so I'm gonna move my screen. So before the main event, I just want to talk about the reversing challenges from last Ninja Night. So there were 3 challenges. I managed to solve 2 of them, and I got about halfway through the third one. So I'll just quickly show you guys what it's all about. So the first one, weirdly, they're labeled opposite. So the first one is actually labeled level 1, and the second one's labeled level 0. So just keep that in mind. Whoops. So, okay, anyway, so for the level 0, which is actually called level 1, what you get is this crackme level1.bin. And if we just open up our terminal here, we'll be able to see what kind of file it is. So if you just go file crackme, it tells you that it's an ELF file. So this is an executable, which means you can really run it on a Linux machine. I don't have a Linux machine here. But if you know about disassemblers, it's pretty easy to take a look at what's inside of this and see what it's actually doing. So my preferred disassembler is Binary Ninja. So typically, if I get anything that's an executable, I just chuck it into there and see what it's doing. So let's take a look. Okay, so we've got an x86 executable, and we'll go to where it enters, so the main function. And here we can see that if you can read a bit of assembly, we can see that it's first calling a function called cCheckPass. So obviously it's going to be checking some sort of password, and then it compares the output of that, which will be an EAX. And if it's non-zero, then it'll take this branch over here and say it's unlocked. The flag is the password. So it seems like we have to enter in a flag inside of this function, and if the flag is matching something, then it'll output non-zero and give us the unlock message. So let's see what's inside this function. Okay, so here we go. We can see that it asks for a password, and then there's an fgets call, and that means it's going to ask us for to enter in the password into stdin. And over here, it's going to be copying with an scanf the password that we entered into a different buffer, this var98. And then finally, it does a string compare with this hard-coded string, which we can see inside the binary. And then if it matches, then it returns 2, otherwise it returns 0. So it's a pretty easy it's a pretty easy reversing challenge. You could probably also find this by just stringsing the binary. But here we go. This is basically our flag here. So if I copy that and enter that in, SecTalks over here, that's the correct flag. Okay, level 1 is pretty similar to that. So instead of getting just the binary, what you get is this zip file. And when you try and unzip it, it prompts you for a password. If you try a few things like password or like admin or something, it's not going to work. And so I just had to search around and Googled for like an online password cracker for zips. And I find this one, which is lostmypass.com, which is a free online zip cracker. And all you have to do is tell it which ones are mountains and hills. So let's give this a shot, see if I can do it first try. Hey, I'm not a robot. Okay, so let's upload our zip file. And let's see what we got. Level0.zip. Okay, so it pretty easily got us the password, luckily. So we hit the jackpot. We know that the password is Jedi. So if we now try and enter in Jedi, now it'll unzip us with a bit of a directory here. There's a few different levels of directories, but here's level 0. And if we navigate over there, we can see that. Let's see what it is. File level 0. Okay, it's a macho executable. So this is actually an executable for Mac, which just so happens we happen to be running. So we can execute it and see what it does. Just assume this is sandboxed, even though it isn't. If I execute it here, it says something fun to get you started. This is the decoy flag. And then it says, don't tell anyone strings is your friend. I think this is meant to be a person in a hoodie, but it's a little bit unclear. Should have chosen a different font. But obviously it's hinted us to use strings, so we do exactly that. Strings level 0. And let's see what it gives us. So there's a few different symbols which aren't really that relevant in this case. This is just the names of functions and various other things. And also like libraries and system utilities that are dynamically loaded. But then if we get over here, just above our output strings, we get this one over here. And you can basically just brute force, try all the different things. This is really the only thing that stands out. But if you try this as the flag, it turns out that is indeed the flag. So let's enter that in. SecTalks. It seems the flags aren't case sensitive in this case, so it's pretty easy to enter it in. Yeah, so that's the first two. Now for the third one, it's one I got a bit stuck on. So it gives us this big text file, which I'll show you guys over here. So it just says SecTalk a bunch of times. And it gives us some pretty heavy hinting that this is written in the chicken esoteric language based on this fun PDF, which I recommend everyone take a look at. Pretty fun. But yeah, so it gives us a bit of backstory and says, okay, he's been yelling SecTalk over and over. So let's basically assume that we've got the chicken language here. And so the chicken language is basically a language that's composed entirely of the word chicken. And it's an interpreted language. So you can basically just download the interpreter, which I already have done. Oops. You can do, Python and pip install chicken py. So I think it's this one. Yeah, so that's how you get the interpreter downloaded. I've just written a bash script that'll call the, where is it? Did I delete it? I think I deleted it. Damn. Okay, so if I remember right, it's user. Oh, there it is. Yeah, it was there. So here's my bash script. So this is basically just Python calling wherever my chicken py executable is. For some reason, that didn't get into my path. So I just I have it hard coded there, and then it takes your first argument and pipes that in. So the chicken py interpreter expects the chicken executable to be instd in, and then it outputs whatever that interprets to. So the only thing left is to convert this to chicken. And so what I did is just run a regex over it, a find and replace. So I took SecTalk, replaced it with chicken, replace all, and then I saved as transcript chicken.text. So when I now run that with the interpreter, chicken pie transcript chicken, that outputs a YouTube link to this random YouTube video, a bit of a meme. What's 9 plus 10? 21, apparently. So this is where I got stuck on. I wasn't sure if maybe the flag was in the comments or something, but yeah, that's pretty much it. Let me just check if any questions have come through. Any?
I guess Jordan, I think, who was the author of this challenge? I think he should be live online now to confirm if the past event was right or was just a red herring, that YouTube.
Was that a red herring? Yeah. Did I get trolled?
Not sure. So just looking at the leaderboard, where is your team standing at? Was it you just solving this challenge, or?
No, so I was in team K17. I just made a new account for these submissions. But let me see. I don't think it'll show my password. There we go. So team K17 is second. Macquarie, we gotta take you down. Yeah. So that's where we are at the moment.
For you, Ben, in terms of
did you try and connect to Nick?
And the other one, which obviously that was a thing there, and the other one is that video is also important.
It's the answer to the question on the service. Oh, okay. Well, next time we'll take a look and see if we can finish that one off. Thanks, Jordan.
Thank you. We also got 2 challenges from Ben. They're not ready yet, but we will release it after today's session. So whoever wants to have a crack at them, you can try that. Thank you very much, Ben. If there are any more questions, guys, feel free to ask them. Now, coming back to our second presentation, the presentation, it was a talk that for a while I wanted to line it up, but as obviously the speaker was not in Sydney, so we got a chance due to this lockdown situation to go and grab our great local speakers across the state. So as you most likely know, our next presentation is from Dr. Yuval Yarom, and most likely you know him from his great work of Meltdown. He's one of the co-authors of the Meltdown attack. He is currently a senior lecturer at the School of Computer Science at the University of Adelaide, and also researcher at Data61 and CSIRO. He's going to have a very exciting talk about the Meltdown attack, the variants of the Meltdown, and the mitigation that pretty much came to the industry since early 2018. So without further ado, I want to pass the stage to our speaker, Dr. Yuval, and in his talk.
Okay, hi everyone, and thank you, Pedro, for the introduction and for the invitation. It's a pleasure to speak here, and the only downside is that I cannot see my audience, and I hope that next year I will be able to visit Sydney and see you in person. So what I want to talk about is a game that we have been playing with Intel in the last almost 3 years, and this is a game of we call it a Whack-a-Meltdown. It started in 2018. We had Meltdown, and Intel came up with countermeasures, and then other things appeared. Lazy FP, if anyone remembers, allowed the attack getting floating point registers, and Intel got countermeasures for that. And then we had Foreshadow and a few more variants of it. And again, Intel killed those. and more came out this year, Fallout, Riddle, Zombie Load, last year. And then this year, finally, we had the LVI, Crosstalk, and the Cash Out. It's not all, I was not involved in all of these works, but only in some of them, but the community had. And this talk is about all this, and the question is, how did we get to this situation that we keep finding bugs and Intel keeps fixing them? And the story starts, first we have a lot to be blamed for, we as academia. Because when we start teaching computer science, we tell people that this is how a computer works, this is the von Neumann architecture. And the von Neumann architecture, we have a computer and it takes instruction from memory, executes them, output to the output, writes data to the memory, and that's how it works. And then we teach computer architecture and we show things that are a bit more complex than that. But we teach high-level languages. And then we are focusing in our teaching on asymptotic rather than concrete performance. And anyway, not everyone studies architecture. It's a minor topic. And we focus on abstraction because that's the important thing in computer science. Everything we do is an abstraction. And CPU vendors have an interest that we don't really know what happens there. Some of that is good because it allows us to move between versions of the processor without too much pain. And some of that is bad. It prevents us from knowing what's happening in the computer. And what this creates is a gap between the way that programmers think about programs and the way that we the computer actually executes these programs. So we'll look at an example. Here we have some program. It's not real assembly, but just for explanation. And this program takes a variable from memory called base, store it in register R1, takes height, store in R2, calculate R1 squared, R2 squared, add the results and calculate the square root, get the hypotenuse of a triangle, and then gets the area of the triangle. Okay, simple program. And when we think about executing this program, what we think is happening is we first execute load, and that gives us a value. And then we execute the other load and gives us another value. And then we multiply one value by itself and we get this square. And so forth, we continue executing instructions one after the other, and we get the result. In practice, what the processor does is execute these things out of order. So the processor analyzes our program, tries to find instructions that it can execute, and execute them when it can. So in this example, it could start with the first instruction. And while it's loading data from base to R1, it might start loading data from R2. From height to R2. And it can happen that the contents of R2 is currently in the cache. So this instruction, the second instruction, will finish first. And when it finishes, we can go and execute a multiply instruction and skip the instruction in the middle. And at some stage, the first load will complete. And only when this first load completes, we commit to everything that we have executed until now. So we get R1 set to 4, and we loaded R2 already, so we can get these two instructions together. And this is great for performance, because what happened is that by the time that normally would take to load base into R1, we managed to load base into R1, we managed to load height into R2, and possibly even managed to do the multiplication. And now we can proceed with the multiplication of R1 because we have the value, and we can proceed with another multiplication because we already have these values. And this process can continue, and that's beautiful because everything that we do, we get to use the processor while we're waiting for all the instructions. Everything appears as if we executed things in order, so the user doesn't notice that, but the program behaves as if we executed instructions one after the other, and everyone is happy. Now, one thing that can happen in this is that we'll get a trap. So suppose we started executing the second load, and height happens to be an invalid address. So this instruction should now cause a segmentation violation. Now, we can't cause this segmentation violation at this stage because the previous instruction, the previous load, has not executed yet. It's not finished executing. So what we do is we mark this as an error, but we continue the execution. And only when the older instructions all committed, we can store the load the value of R1. We can note that we loaded R1, and we can now raise the trap. Okay, questions so far? Perfect. So with that, one other thing that happens is that while we are waiting, it's a bit difficult, apparently, to stop this instruction and everything else. And what happens is that dependent instructions start executing. So now what happens is that we'll have this multiplication of R2 by R2 with some data that we got from an instruction that failed. And hopefully this is not a problem, because this instruction will never commit, will not really write the square to R4. As soon as we raise the trap here, all the instructions that executed below it will disappear. So nothing bad happens, right? So unfortunately, what we have found in late 2017, published in early 2018, is that this is not as simple as that, and there are problems. And we'll look first at Meltdown. This is the only attack that I will show in details how it works. The rest I'll just discuss because we don't have the time and the details become really technical. So let's look at Meltdown. The code for Meltdown, and I'm moving to C here because it makes life easier. We have two lines of code. The first does pointer dereference, and the second does a dereference of an array with a value that it got from that pointer. And for the first example, we'll see. Okay, so first, why do we have to wait? Let's go to the code there. Suppose that we discover here that this fails, right? This instruction fails. But things before it has not finished executing yet. We are still waiting for them to execute. If we stop everything now, then the program is not in the situation that or in the same state that it would have been had we executed the instruction one after the other. And now the user cannot reason about what has happened when the instruction when we got the failure. Now, these failures do not necessarily mean that the program should crash. So in the case of a height not being mapped, the program should crash. But another example could be that the page that holds the contents of height is paged out, and the operating system should take control, bring it into memory, and continue the execution. And what we want happen is that the operating system at this stage should be able to know what the state of the program is, to be able to recover the state when the page is back there. So we must wait until it is this instruction's turn to be executed before we can actually stop the program. Okay? Cool. So we have this scenario, and for now, let's assume that we have the pointer here. It points to some location in memory that has 3, and we have our array in memory. And for the discussion, let's look at the state of the cache. Let's assume that this 3 is cached in the L1 cache. Our pointer is cached, and our array is completely not cached. And now we start executing. So we do a pointer dereference. This gives us a reference into the array, and accessing this location will bring it to the array. And now we'll do something that we don't really need. we'll try to find what value we got here to I without actually looking at I. And to do that, we'll call an old friend, count. Remember him? And count, what he will try to do is do whatever count does, trying to guess the number of the day. And the first thing is it 1? It will check whether it's 1. It will access location of array of 1 times 256 and measure how long it takes to get the data. And because this is not cached, it will take a long time. And then our count will ask whether the number is 2. And again, because it is not cached, the location 2 times 256 is not cached, it will take a long time. And then the count asks whether the number is 3. And this location is cached. So the count learns that the number is 3. And now we have all the balloons falling and everyone is dancing. Now this is a bit weird. So let's change the scenario a bit to see why we really need to see I like that. As you know, processes in most operating systems until in the end of 2017, the address space was divided into 2 parts. One part was for the program, and that's where the program executed. And another part had the kernel, the operating system kernel. And this part was protected by a bit in the page table that prevented access or prevented users access to these addresses. And the reason that we want to do that is that it improves performance. When we need to call the operating system, all we need to do is change the privilege level of the processor, and then we suddenly can access the kernel and we have access to all the data, and we don't need to start copying data between address spaces. So now let's assume that our pointer points inside the kernel. So we start executing this instruction, and it dereferences this location and it finds the value is 3. Now, as we discussed earlier, this instruction will fail because the user is not allowed to access this location. But between the time that the instruction fails and the time that the processor actually acts on this failure and stops the program, some instructions that follow this access will continue executing. So what we will do now is we will dereference array with this value, and that will bring the data into the cache. At some stage, the processor will realize that this instruction needs to stop and will say, hey, everything that happens after this instruction did not really happen. We are throwing all the data out. So all the results that we computed are disappear. But what doesn't change is the state of the cache. And now what we do is we bring count again, and is it 1? And it's not 1, it is 2, not 2, and is it 3? And we found our number. And this is a great primitive because it now allows an attacker to read every location in the kernel. And not only we find information about other processes, modern systems to facilitate their operation map the physical address space into the kernel virtual address space. So basically what we can do now with this primitive is read every location in memory. So that includes every other process that runs there. Can get passwords, we can get private information from browsers, we can get almost whatever we want if we just work hard enough to analyze the data and to trace whatever pointers we find there and use. So that's Meltdown. And basically, Meltdown, what we have is, to summarize Meltdown, we have the fact that errors in instructions are not handled immediately, so there is a delay. Instead, the processor waits until the instruction commit. And then, while it waits, other instructions, other dependent instructions continue executing, and they continue executing with data that came from somewhere. and leak this data, and we can leak this data through the microarchitectural state. So what's the immediate solution? The immediate solution is, let's look at this unsanctioned data and prevent access to it. If we prevent users from accessing secret data, they cannot leak it, and we are protected. So for Meltdown, we have two main countermeasures. The one that we use for older processors it's called KPTI, but basically what we do is split the address space between the kernel and the user. So we take our original process, and now we have an address space for the process that has no kernel or has very little kernel, and another address space that has another copy of the process memory and the kernel. And whenever we have a system call now, we go to the little bit of the kernel that we have there, and this switches the address space, the kernel executes, switches back, and the process can continue after the return from the system call. This works, this protects, but the main problem with that is that we have an overhead when crossing address spaces. This overhead can amount to 30% performance, depending on the processor generation and the workload. For newer processors, Intel didn't want to do that. They wanted us to continue using the shared address space. And what they did is a simple countermeasure that whenever there is an instruction that fails when accessing the kernel, the dependent instructions continue execution, but they continue executing with a value 0, irrespective of what was in the kernel. So we are secure. We are not leaking any sensitive information. We can read zeros from the kernel, but we know that we can read the zeros, so it doesn't really matter. The main downside of that is that it requires hardware changes. We need to buy new processors. So are we protected? Obviously, because I wouldn't have done this talk if we would have been protected. And here comes foreshadow. And by the time that Intel published the results on Meltdown, and the defense for Meltdown, Intel was already aware that they have foreshadow and they needed to protect against other things. So foreshadow, or in Intel name L1TF, shows that actually the problem is not only that we can cross the user and kernel boundary. There are other boundaries that we can cross, and there are 3 variants of foreshadow. Foreshadow OS basically says that if a page is marked as non-present, we can still read data from it if the physical address maps to a physical page. So if we take a page table, it maps to a physical address, and we access that page, then we can read the data there. And this is a security vulnerability because most operating systems, what they do when they page a page, when the page is paged out, the only thing that the operating system does is mark this page as non-present, and then when the user tries to access that, we'll get an exception and we can bring the page back in. And so when a page is paged out and another process gets the same physical page, we can start reading data from different pages. We don't have much control about over what we get, but we can read data, and that's a risk. Second one, foreshadow VMM is much more interesting. When we translate addresses from in virtual machines, the address translation occurs in 2 steps. We first translate from virtual address to what's called a guest physical address. So it's a physical address as the virtual machine guest sees it. And then there is a translation between guest physical address to real physical address, to host physical address. And it turns out that if the translation to guest physical address fails, then the load instruction continues happily by loading from whatever physical address the guest physical address is. So the operating system that runs inside the virtual machine can control the host physical address that it reads through with foreshadow. And that's a real risk because it allows a virtual machine to read whatever is in the physical memory and that's other virtual machines. So if we're running on Amazon cloud, we can read whatever other people that share the server with us can execute. This is not that bad because we need the data to be in the L1 cache, so we only can read data of processes or of VMs that share the CPU with us or that they executed just before we start executing. But this is a risk that we need to take care of. And the last is foreshadow SGX, and it shows that data that is in the L1 cache data from SGX that is in the L1 cache can be leaked. And SGX, for those who are not familiar, is a set of extension in Intel processors, software guard extensions. And what that allows us to do is to run software on the machine such that the software is protected from everything, from any process on the system, from the operating system, from the hypervisor, and from the SMM. SMM, don't remember, secure memory management. I don't remember what it means. And Intel promises that this way we can run our software in the cloud and without the need to trust the cloud provider. The real reason is probably not that, or the real reason that Intel develops SGX is probably to protect media so that Netflix can show movies on our computers without us being able to look at these movies. But we have SGX for that. And apparently what happens with foreshadow SGX is that it allows us to get data from SGX, and we did the work on that to the level that we managed to break the whole mechanism that ensures to remote users that the system runs on SGX, and now we can break the whole SGX ecosystem. So we had this is basically the same problem as Meltdown. Address translation fails, or we hit something that is illegal, and still we can get data that if this data exists in the L1 cache. So what did Intel do to protect against foreshadow? For foreshadow OS, they added to the operating system what's called PTE inversion. So when we set a PTE to non-present, we store all the bits with 1. So we invert all the bits of the physical address. This leads to invalid physical address, so nothing leaks there, and we can revert that when we bring the page in just by inverting the bits again. For virtual machines, we have a new instruction that flushes the L1 cache on VM exit. So when the hypervisor goes back to the VM, it flushes the L1 cache, and we are guaranteed that the hypervisor, the virtual machine cannot see anything that happened before it started or it resumed the execution. And to handle multiple virtual machines running on the same core, and 2 hyperthreads of the same core, the hypervisor was changed, so it ensures that only trusting VMs run on the same core if we want to have high level of security. And that ensures that we don't leak between the two. If we leak, it doesn't matter too much. And for foreshadow SGX, there is an update to the microcode that cleans the L1 cache when SGX goes back to the operating system. It adds support for detecting hyperthreading, so the user can know that the SGX enclave runs on a system with hyperthreading enabled. But it stops short of claiming that hyperthreading is not safe. We know that it is not safe on machines that are vulnerable to this attack. But Intel didn't want to admit that. So these protect most of the things that we want, and we start seeing a pattern in the protections. The main thing in the protections that we have is either we do software to prevent access, which costs us, or we add instruction for flushing data from the locations where it leaks from. And again, on newer processors, this doesn't leak by zeroing the data, so we have a third mechanism that if we have that sensitive data doesn't go through these failed instructions anymore. So, but the question is first, have we solved the problem? And of course, we haven't. And this brings microarchitectural data sampling, MTS attacks. It's a group of different attacks that the main finding is that the data leaks not only from the cache. So if we have some of our processor, we have our execution engine that executes the instructions, and we have the memory pipeline that has the L1 cache and the L2 cache, and then below we'll have the last level cache. And there are some buffers that are used for various purposes. So line fill buffers are used to bring data into the L1 cache so that we don't need to wait to lock the L1 cache when we have a miss. And the store buffers take care of ordering instructions. When we have loads and stores that execute out of order, we want to make sure that if we store data into memory, the following load will get that data, even if we try to execute it before executing the store. And both Meltdown and Foreshadow read data from the L1 cache. And MTS attacks show that we can read data from the line fill buffers, we can read data from the store buffers, we can read data from a component that's called load ports that I don't show here in the diagram. It's nice we get this data. The downside is that we have much less control over what data we get. We just happen to get data that was in transit in the processor. This doesn't prevent attacks. The Riddle work showed how they can leak /etc/ what's the name? Shadow. So they leak the encrypted passwords from shadow file and then continue, and then they can use it for attacks, for example. But so we still have data leaking. And there is a bonus. We showed that we don't really need traps. We can also do attacks with what's called microcode assists and with TSX aborts. Microcode assists are conditions that happen when executing an instruction, and the instruction cannot complete successfully by using the hard-coded or the fast path, and needs to do complex processing. An example of that is if we try to access memory, and this page is marked as unread. So getting the data from the memory needs to change the PTE entry to mark this page as read. And now we have a problem that if we do this asynchronously, we don't know whether the execution will reach this point or not. So we need to stop the execution here and move to completely synchronous execution to ensure that we know what the situation is. And the way to do that is we stop the instruction as it runs, and we tell that it's very similar to an abort or to trap, but the processor automatically resumes the instruction in the right way. TSX is another extension in Intel, and what it does, it allows us to combine multiple instructions together into a single transaction, such that either the transaction exists and all instructions execute successfully, or the transaction does not exist and all the instructions and none of the instructions executed. And this is good for if we want to implement locking between multi-threaded applications. We can start executing optimistically as if no one contended with us on memory, and if things fail, then TSX will tell us. And if a TSX transaction aborts in the middle, well, then some loads may create the same behavior that we saw in traps. So what we have so far, we have a set of bugs that work, and we have our conditions that caused these meltdown-like attacks, and our countermeasures prevent access to sensitive data, flash buffers, zero sensitive and zero sensitive data. So mostly for MTS, what Intel did is it gave us instruction to clear the line fill buffer and the store buffers. And the assumption is that for concurrent processes, because we don't have any control of this data, we are relatively safe. So are we done? Of course not. We are moving to early this year, and we have cache out and crosstalk. So if we look at our memory, well, let's look a little bit down we have the last level cache here, and we have a staging buffer that the processor has, which is used for certain instructions like CPU, like CPU ID and random RD-rand. I'm not familiar with the centralized repository of POCs for these. The people who developed most of these, there are some POCs around. So there are POCs for the guys in Graz have POCs for Meltdown and for Zombie Load. The guys from Free University have for Riddle and for others. If you send me an email, I'll send you the links. I don't remember them. So it turns out that now we can, what we can do is we can take data and move it from the L1 cache to line fill buffer. That's cache out attack. Or we can take data from this staging buffer and move it again to the L1 to line fill buffers, and this is what's called the crosstalk attack. And because we can move data from the L1 cache to the line fill buffers, when say SGX gives us control back after freeing or after flushing the line fill buffers, if it does not flush the L1 cache, we can move the data from the L1 cache back to the line fill buffers. And unfortunately for Intel, some Coffee Lake machines came up with, assumed that they have protection for shadows, so they did not flush the L1 cache, and we repeated all the attacks on that. For the staging buffer, this staging buffer is used for multiple instructions just to prepare the data for them. So when we run CPU ID, it puts some data in the staging buffer and then move it to the line fill buffer from which CPU ID gets it. Similarly, if we run a RD-run, the instruction that generates random numbers, it puts it in the staging buffer and move it to the line fill buffers. And it turns out that if we do CPU ID and then we do MTS attacks, we can get the data of previous RD-run from the staging buffer. So this allows to steal randomness from SGX, and because randomness is the basis for protecting cryptography, we can use that for an attack. And the last attack that I'll talk about is LVI, load value injection. And what happens in LVI completely reverses the way that we do the attack. So instead of trying to leak data and find what the data is, we're trying to force the victim to execute, at least transiently, at least out of order instructions that will disappear later, with data that it is not supposed to execute. And for this, for example, if we have a return instruction at the victim, return reads data from memory. And if this read fails, for example, because of microcode assist, the victim will get whatever data they find in the line fill buffer, or they'll get 0 if the processor zeroes this data. And it turns out that if you start zeroing or changing the return address, then you get the processor to execute whatever address that you want them to execute. And we can find somewhere in the victim that leaks data and use that to leak whatever data we want. It's not an easy attack to pull off, but it works. Particularly, it works against SGX. And the fix for that is Intel replaced every return instruction with something that ensures that that there is no speculation beyond return. Every jump instruction is not speculated beyond the jump. So we have a quite complex code, or the compiler for SGX now is extremely complex just to get. So why did we actually end up in this scenario? We have what we said so far, and we had the error instructions that are not handled immediately. We wait, and we get access to unsanctioned data, and the fixes try to prevent this access to secret data. But this is not the real problem. The real problem is not that we get access to unsanctioned data. The real problem is that we have abnormal execution after abnormal termination. And whatever execution here will be with data that we are not supposed to execute with. And when we execute with something we are not supposed to execute with, it's similar to buffer overflow. Suddenly we have data that the programmer did not expect, and it's hard to handle that. It's hard to reason about that. And there are multiple ways that we can exploit this. And this brings me to what we suggest now as the solution. And the solution is basically is very simple. Don't do it. Just avoid execution after an instruction aborts. And there are two possible ways of implementing that. One of them is we had already dependent instruction waiting for the data. If we don't tell it that it has data, then it will not continue executing. Another option is we can keep a mark on each unit of data, whether it is a legal data or valid data or invalid data. And if it is tainted, we don't execute. We just bypass the execution units. Now, it's very easy for us to say that we can do that and it will protect against all these type of attacks. It's extremely hard to implement this. One of the reasons that it's hard to implement is that CPU redesigns take a long time. This code or these changes are changes well into the CPU pipeline. So there are complex changes. They will take time for validate. It will take time for manufacturing, testing, and probably will take between 3 and 5 years until the problem is fixed. We started 3 years ago, so we expect that next year or maybe a year or two later, we'll have a fix. So to sum up, we have errors in instructions are not handled immediately. The processor allows dependent instruction to continue execution after an instruction fails, and that resulted in multiple security vulnerabilities. Countermeasures so far address the symptoms of the problem, not the cause, and therefore they are not successful. And I can't complain. It got me 5 papers, and this is the for academics, this is our currency. So it has been really useful for me. But for end users, I don't think that this situation is the best. And we expect better countermeasures in a year or two. Regarding other architectures, so RISC-V is not a single. So the problem is not in the architecture. The problem is in the implementation. So we can't say about RISC-V whether it's vulnerable or not. We can ask whether a specific implementation of RISC-V is vulnerable. Same we can ask about ARM. In practice, what we know is that no such vulnerabilities have been found on AMD. On RISC-V, I am not aware of any processor, so I am not aware of vulnerabilities in the RISC-V. On ARM, there have been some ARM processors that were vulnerable. So again, I don't remember the details, but they were vulnerable to the initial meltdown. I don't know to what extent people tested for other bugs there. We haven't succeeded, the bugs that I was involved in, we haven't succeeded replicating on ARM. So that's it. Thank you for listening. And if there are more questions, I'll be happy to take them.
Thank you very much. That was, quite a short time to go through all those complex attack scenarios. Thanks for taking the time to explain through those. I have plenty of questions, but if there is any questions from our viewers, please feel free to post it on the YouTube chat or the IRC channel or the Slack. Otherwise, I will start cracking my own questions. The first one, well, let me ask the second one first. I think it was a slide number 40, and you talked about the TSX abort, and you mentioned, is that issue with the TSX abort? Maybe we go to that slide again, number 40. Was it here, or was it maybe... You talked about micro ASICs.
No, earlier. Yes.
Again, is this the cache issue, or is it just...
What we have there, the way that we pull the attack, the way that it's easiest to pull the attack, is you take a memory location, flash it with CLFlash, then starts a TSX transaction that accesses this memory location. Now, TSX needs to keep a track of which memory locations it accesses, so to ensure that there are no conflicting accesses. And so what happens in the middle of this load, TSX realizes that this memory location suddenly is moving out of the cache, and the loads terminates in the middle with an error, and then we can get data from certain buffers. So we can't, with TSX abort, we get mostly data from the line fill buffers, but we can get from other buffers. It can only work from transient buffers, not from the cache itself, because if the data is in the cache, then the load will not abort in the middle. It will get the data, or it will abort before the flash. So either the flash will happen before the instruction, and then we'll get the data as we need, or the flash will happen after the load, and then the load already got the real data.
Okay, so the concept is similar to the concept of the SYD or transactions that we have in the other fields. So once one of them failed, you need to invalidate all the previous kind of your processor or your system need to revert back to the original stage. But in this case, it seems like everything being cleaned up except the cache. And over there, we have the issue that the next instruction will leak out the info out of it.
Yeah. So what happened with the cache? So the leak, all the leak we do through the cache currently, because it's easy to leak things through the cache. But there have been works that show that we can leak data in other ways. We can leak data by monitoring the execution flow. So if we take the secret data, and based on whether it's even or odd, we do either additions or multiplications. And we can leak data just by finding which execution unit was executed more, or was executed during the attack, the transient part, so executed out of order. So we do get data leaks that are not through the cache. And also, when we say that the processor reverts the state, it's not really reverts the state. What the processor keeps track is, it keeps track of what the state is, and it only moves this. So it has a microarchitectural state that is the state of real execution, and it has the state as the user or the program sees it. And it only updates the states that the program sees when an instruction ends. It doesn't calculate something, put it in RAX, and then revert it backwards.
Mm-hmm. All right. Okay, I got a moment to think about this. So what you're referring, so cache is not the issue here, like, because one of the things I wanted to ask you was, do you think by, let's say, simplifying everything, let's say, obviously we're gonna impact a lot of usability in this case, just getting rid of that cache, would that solve the issue from your perspective?
So I think that getting rid of the cache will not solve the issue. Getting rid of any state when we cross security boundaries will solve at least these issues.
Mm-hmm.
Wait, no, sorry. It will not solve. No, it will not solve, because we're still within our security boundary. We are the same process that does that. But if the microarchitectural state does not leak, then we are protected. But we don't know how to even test the microarchitectural state, whether it leaks or not.
So we got a question here.
Yes. So the way it works, Intel can execute up to around, well, it depends on the processor, 200 to 300 instructions to the future. micro-ops. It's not real instructions, but it's several hundred instructions. And if the processor discovers that you're down the window 300 instructions into the future, there is an instruction that fails there. It will take it about 300 cycles to get to the top and disappear from the pipeline.
Okay. See if we have any more questions to ask. Now, one of the things you mentioned, this is around executing all these instructions in order, or some of them will be executed, like as you said, in terms of Intel in future, like around 200, 250, as you described. Now, have you considered like the cases where there is due to a type of fault, the CPU at some stage does not, like is going through one of these transactions or one of these instructions and it fails, and then it doesn't get a chance to clean up the cache or XOR the cache? Would that be another trend of the attacks, that just because of the processor, although there is some sort of security mitigation around in terms of like going up, cleaning up, or XORing the cache, that will not get a chance to get executed at all? So all these attacks again comes into the place. I'm trying to refer to the previous talk by Dr. Peter Gottman, which he was talking about all these faults and the deterministic nature of the non-deterministic nature of the program or the processor when these faults happen. And we can't really guarantee that this loop or this condition will ever end. So we are in some sort of situation where some of the instructions are executed, but some of them are not. And then we cannot really say about the state of the program. So I guess coming back to these attacks that you explained, do you think that we're going to have those situations?
So this is gut feeling because I don't know. My view is that as long as we do not address the real core of the problem, we will have a problem. We are still exposed. There might be something there. We don't know what it is. We currently know, I'm aware of a few other attacks that are not public yet. But the thing is that as long as we rely on the fact that we clean the state between when crossing security domains or security boundaries, then we might miss something for whatever reason. Either a fault is much more difficult to do in these processors, but it can happen. And or there may be some complex scenario that Intel has not considered that will not clean things. It can happen. It's not as if Intel never made mistakes.
Because in the way that you try to, my understanding that you try to model the problem, the issue going back to that abnormal instruction or that invalid instruction that shouldn't be executed anyway, and that since it is being executed, then we have all these other challenges to go back and clean up and to fix it up or revert back, not in a real sense.
Yeah.
And in the terms of fault is a similar story. Like one of those instructions will either not get executed completely or get executed halfway. So effectively, we are reaching to the same like problem here, and that could cause all these attacks again, bringing to the surface.
This is the same. Look, the class of this problem, it brings us to when programs start to execute with data they were not supposed to, or data that they did not anticipate. And what we get is that all the reasoning that we have done about the correctness of the program and the what data it might reach and what it can leak and what it can do, all these reasonings disappear. We suddenly don't have anything. And this is the same as the next question about the return-oriented programming. It's once you start to do something different, then the whole behavior of the system is unclear, and we can reason about it when we know what's happening, and that's how the attack works. But we can't reason about things that we don't know. And yes, about sorry.
Yeah, go on, please.
Yes, about the return-oriented programming. We like to compare mainly Spectre to return-oriented programming because in Spectre Spectre is a bit different in that it doesn't use failed instructions. Instead, it used misprediction. And there we can just chain a set of, we call that gadget based on return-oriented programming, a chain of gadgets that would leak the information that we want. With LVI, we can do that as well. It's a bit more difficult, but that's the way LVI works. There is a limit to this is only limited to data leak because whatever happens in this out-of-order execution domain, what we call the transit domain, the instructions that shouldn't actually execute, is limited to some very short time. So we have 300 cycles, that's a few nanoseconds. And once it terminates, all the data that happened, that really we saw there, disappears. We don't know how to cause anything that will affect the architectural state. We only affect the microarchitectural state, and the microarchitectural state, we just get information about what it is. We don't change it in any malicious way. So we will not be able to do arbitrary execution and write data to the disk.
Okay.
Shell code does not exist here.
Yeah. Do you feel that because often when there is a trend of all these type of the exploit developer, they come up with a new POC, and then on the other hand the defenders they come up with a mitigation, and this Whack-a-Mole game which is the title of your presentation, it's a trend in our industry. It will be for a while like this until someone come up with a solid plan. Now, from your experience, do you see the problem of Meltdown or these kind of side channel attacks? Is it related to that we haven't modeled the problem properly, so that's why we don't come up with a better solution, or you think it's just too difficult? We already know what is the problem, but we can't find it. We can't implement it. It's just too costly.
So for Meltdown and all the attacks that are what we call Meltdown type, all the attacks that depend on an instruction failing and then things continuing, I believe that there is a solution. It's easy to describe it. It's hard to implement just because we have 10 billions of transistors inside the processors, and implementations there are not easy, and it's physical, it's not software. So it will take time, but I believe that all these sort of attacks will disappear in the next or the one after generation of processors. And we will not have them except with bad designers. So it's the same as buffer overflows. For buffer overflows, we don't have a real solution, at least in unsafe languages. But we have safe languages, and theoretically the problem should disappear, but they do not. I don't think that we'll see any 5 years in the future. I don't think that we'll see these kind of problems in the major chip vendors.
Mm-hmm. So I guess
not Meltdown. Spectre we will. Spectre is here to remain.
Very interesting. So I guess what you're referring is there is a problem that is already in the design of these CPUs, and then until that design flaw is not addressed, so we already know the problem. We already have modeled it properly. The reason I'm saying it is because in a lot of other fields we haven't modeled the problem very well. Like going back to the issue of input validation and why all these programmers are not validating the data properly. If you really look into it in detail, you will find that we actually haven't modeled the problem properly. And all these things that we are just offering in all the other mitigation controls, filtering, sanitization are actually not addressing the problem. And no wonder it's 2020 and still there are codes out there have an issue with the buffer overflows and all the web type attacks.
SQL injection.
Then coming back to the cache, cache. You talked about in the microprocessor perspective, the cache is a problem in the other higher level layers, like in terms of web, in terms of other network services. There are attacks against caches in general. So it seems kind of drawing a very quick conclusion here that let's get rid of those caches. So you're going to solve a lot of issues, but obviously that's not going to be the solution.
Oh, look, we have a problem that all the software is too complex for us. We are writing software that is more complex than we can really reason about. And we try to do that, and we write if we have good abstractions, we manage to do things better. But the bottom line is that it is all too complex. There are so many things. We are not designed to follow every detail. We are just creatures of intuition.
Yeah. It's very non-deterministic, as one says. Well, I guess perhaps the final concluding question for anyone who is interested to look into this further, both from an attack perspective or mitigation, what sort of things you would suggest as well of the background knowledge or things they need to learn, or any references?
So we have the paper
from Intel manual, I guess.
That's what we read. And the Intel manuals and the patents, I can tell you, when we did this, when we read those, I slept really well. You start reading that and fall asleep. I think that, look, research papers, I think, for me, I find they are the best thing to read because they have all the information. It takes some practice and experience to get into them. So first time people read research papers, it's not as easy as we ought to make it. We would love to make things easier for people. Sometimes we succeed, sometimes we don't. So, yeah.
Research papers, books?
There are no books about that. So the attacks are too new for books to have. So there are books that have a section on Meltdown and a section on Spectre, but the details and the real understanding of this is not there.
Well, I guess someone also, in terms of like background info, like in terms of like model of computing, I don't know, Turing machines, things like that, would you suggest those things will be kind of foundation knowledge someone needs to know before even getting to understand why we have these many different types of cache in the CPU and things like that?
There are architecture books, so where do I have them? I should find them. I'll find it later. There are some books on computer architecture, but most of them do not go into these details. So there is no real single source of information. If anyone is interested, I'm looking for PhD students.
Do you offer a scholarship?
Depends on the student and the time of year. If people come at the time that we have the money, yes, we offer scholarships.
There we go. That was, I think, the best offer then.
Yeah. Honors, masters, PhDs, everything. So we are looking for people who have technical skills. And people who know how to do that, learn how to do that in other domains. So how do people learn to do SQL injection? How do people learn to write shell code or return-oriented programming? Do that several times. It doesn't work at the beginning. You start with simple examples, and after some time, you get better. There are books, but the books don't have all the information. They are not sufficient.
Definitely, yeah.
So doing is the way, and I think that the good thing with doing it with us is that we are at the edge of the knowledge, so you get quickly to where people are, to where the knowledge is, the boundaries of knowledge are.
Beautiful. No, that sounds great. Let me bring Ben up as well. So thank you very much, Yoval. Thank you, Ben, for your presentation, and thanks to all our viewers. This was our last SecTalks of 2020. As I mentioned, there is a feedback form like previous years to gather your thoughts, comments, things that you would like us to do in the next year. If you would like to help us organizing SecTalks in 2021, please also let us know. Otherwise, all the best, and you're gonna hear from us again soon.
Thank you.